Okay, I'd like to welcome Tom Adams. He's a professor at NTNU, formerly at McMaster University. He's had a long history in the process systems engineering area and in modeling, simulation, and design of sustainable chemical and energy processes, including power generation, carbon capture, synthetic fuels, alternative fuels, advanced distillation technology, mobile and modular chemical plants, energy conversion, and techno, eco-techno-economic analyses, and others. Okay, so one of the things that he has done is published several books. We're going to hear a little bit, hopefully, about his Exergy Handbook, but he's also published Learn Aspen Plus in 24 Hours. But even more importantly, he's really fostered a sense of community within process systems engineering. He runs a psecommunity.org website, and that has the living archive for process systems engineering, or LAPS. And it started as a CAS-supported project. He's had several awards. But just going back to that LAPS project, Tom, I saw last year, I think something like 38,000 submissions to that website. Is that right?
That's true, but there was a sort of backhaul of a journal that joined, and we indexed a bunch of their stuff. So
Oh,
that's what that
fantastic.
was. Yeah, so we had a good year. Yeah.
Well, it's indexing, but also, data sets or other things that you can post to be able to archive them permanently so that they are reproducible and we move this field along. So he's made fantastic contributions, both individually, but also fostering the sense of community. We look forward to hearing from Tom today.
Wow, thanks a lot. That's a really nice introduction. So it's always a pleasure to talk with you and your entire crowd of students I can see on Zoom as well. So that's pretty fantastic. So I'm really happy to be here. I'm excited to talk about Exergy today. And, this is a topic that this is something I never learned as an undergrad or grad student, but it was something that I really wanted to learn because I felt that there was something to it that if I could just master it, if I could really understand it, I would be a better systems engineer. So I worked really hard to learn it, basically. And everybody I talk to, when I ask about Exergy within the system community, everyone says, "Oh, yeah, I've always wanted to learn that. I never really understood it. I've heard about it, but I tried. It's just impenetrable or too hard." And it's really too bad because I think it's an incredibly useful tool. And so the whole point of the Exergy Tables book is really to make it accessible to everyone. So for researchers and practitioners, you don't need a PhD to use Exergy. So I'll talk about that. I'm going to talk about how useful it is within systems engineering because I feel it's an incredibly useful toolkit, and we're going to start changing how we do analyses, how we design, how we optimize, because we're going to incorporate Exergy as one of our main tools, I think. So this is where I think it's really exciting going forward. So just a quick introduction to Exergy. So the book, Exergy Tables, all right, you can get it. It's McGraw-Hill. If you have Access Engineering, I don't know if you do at BYU, but a lot of universities subscribe. It's like a Netflix for books, and it means that all of the students can have it for free. And then I get paid per download, so it's like a super good situation. So everyone gets to use it. But it's really Exergy in plain language. I think that's the best thing. It does talk about the thermodynamics to a degree. You have to. It shows you how to use it, but most of the book is tables and charts of numbers. The reason why that's important is because if I were to hand you the number, like the Exergy value of a stream, you could use it right away. That part's not hard, but calculating that is very difficult. So the whole point of the book is you just, you learn about it and then you look everything up. And it doesn't have everything. We've got thousands of chemicals. We got all the different, many different kinds of fuels, solids, liquid gases. And so it cuts down the work by a huge amount. So the point of the book is to get over the biggest barrier that people have, which is the barrier to entry and calculating values. That's the point of the book. And then you're off to the races. Okay, so Exergy in a nutshell, for people that have never heard of it before, the best way I can describe it is it measures both quantity and quality of energy. Okay, so it's measured in joules or calories, just like other kinds of energy. But the quantity part is based on the first law of thermodynamics, and the quality part is based on the second law of thermodynamics. Okay, and so Exergy is kind of a marriage of the two. So here's an example. Let's say I have water and an Olympic-sized swimming pool at 28 C. Okay, so it has thermomechanical energy in the form of like the heat capacity, let's say between 28 and 25 C, or I can have 8.3 megawatts of electricity. All right, both of those have 30 gigajoules of energy, I mean. Okay, so they both have the same amount. However, the Exergy content of that tepid water is just 0.15 gigajoules, but the Exergy content of electricity is 30 gigajoules because electricity is basically pure Exergy. Okay, so they both have the same energy content, but clearly the quality of electricity is far beyond the quality of tepid water. Okay, so like what can I do with my electricity? Well, I can power a Canadian house for 6 months. I can drive an electric car 47,000 kilometers, which is unbelievable but true. Okay, or I can heat up an Olympic-sized swimming pool by 3 degrees. Okay, I can do all of those things with 30 gigajoules of Exergy. But what can I do with 30 gigajoules of energy in an Olympic swimming pool? Well, I can swim in it. Okay, so like obviously this is more useful, and Exergy is that thermodynamic measure of that. Okay, so we're trying to quantify that now with something that means something to us, and the point is for us as a systems engineer to use it for decision making and to understand and analyze. That's the point. Okay, so there's actually a bit of an argument in the literature about the taxonomy, like different kinds of Exergy and how you break it down. I don't want to get into too much detail, but we really focus on heat Exergy. This is a very common, everyone kind of starts there. So our book talks about this. And I want to make very clear, we're talking about Exergy of energy on Earth, because Exergy is relative to the environment. Okay, so if 30 gigajoules of something is 30 gigajoules wherever it is, if it's energy. But if it's Exergy, it depends on how in comparison to the environment. Okay, so we have to be very specific. We mean the Earth. And we talk about substances and matter. The two that I'm going to really talk about are thermomechanical Exergy, which is things from like the thermal energy, pressure-related energy, but it's a little bit more than that. It includes phase. And then the chemical Exergy. So that's like the chemical bond energy, the potential there, but also concentration differences from the environment as well. So purity. So these are all lumped together in these two forms, thermomechanical and chemical. We add them together and we get conventional. And we have things like we can add things like gravity and motion, but we're not going to talk about that today. All right. So there's a big correlation here between these values of Exergy and monetary value. And we'll talk about that as well. So there's a very, very useful connection there. Now, the definition of Exergy, now this is already argued about. Okay, there's different sort of academic spheres based on what definition you work on. Like it's almost like a family. Which family are you in? And this is important. I don't think people talk about the definition enough, but the best definition I can find that I think makes the most sense and is that Exergy is the maximum theoretical work obtainable from an overall system consisting of a system and the environment as the system comes into equilibrium with the environment and then passes to the dead state. We're not going to talk about the dead state, but this is a very common working definition, and it basically means I have something, a system, like I care about a chemical. I'm really concerned about substances, so like my chemical, and then I have my environment, and I can do work if I can bring my thing into equilibrium with the environment. Okay, like if I can bring it into equilibrium and do work in the process, then I'm producing work. Okay, and the max amount of work I can do is what we call the Exergy. I'm going to use TM because I'm going to talk about thermomechanical Exergy mostly today. All right. So all I did here was I just rewrote it as an optimization problem because I'm a PSC person, and a lot of people are going to understand this immediately when I express it this way. This is not common to write down actually, but it's what we mean in mathematical terms, right? I should be able to find a process P. Okay, that's my decision variable that brings my system into equilibrium with the environment, and I should be able to do work during that. And so whatever process solves the optimization problem, that maximum work is my Exergy. Okay, so that's another way of looking at it. And just for the sake of discussion, I'm not going to talk about this, but we're talking about open systems, so they're flowing, they're practical things chemical engineers care about. So you can allow mass to exchange with the environment. That's just a caveat for the nature of the class of equations I'll talk about today. Okay, but we can this optimization problem we can understand, I think, and that's our perspective. Okay, so that process P, you can exploit any difference between that and the environment. So I should be able to exploit a temperature difference, a pressure difference, but phase differences, concentration differences, chemical form like bonds. I can exploit height, momentum, all sorts of stuff. If it's different than the environment, I should be able to exploit it thermodynamically in some way. Okay, so for example, real simple, let's say I have something that's hot. One way I can exploit the heat of that thing is by building a heat engine, like a Carnot engine. Real classic thermodynamic result. I can use that heat if it's above my reference temperature. That's my environmental temperature, T0. All right, and I should be able to use like a perfectly reversible engine. I can produce work, and then I reject the remainder of the heat of the engine to my environment. Okay, so, and I could do this until, like if this is closed or something, I could just leave it until it finally cools to the environmental temperature. Okay, this is a very normal, simple thermodynamic result. Same thing for pressure. If I have something at high pressure, I can let it go directly in the environment through a turbine producing work, right? These are very normal things that we do in engineering. So these both have exergy, and these are different ways I can exploit that energy involved, okay? But I can do more than that, because if I have a heat sink, if I have something below the reference temperature, below the environmental temperature, okay, my surroundings, I can pull heat from my surroundings into my system and produce work in the process. Okay, we do this all the time in LNG regasification. So you have your liquid natural gas goes to terminal. They need to heat it back up, but it's very cold. So they use air or seawater to power that heating, but they can run it through turbines. Like you can just imagine air going through turbines as it warms up a cold LNG. So this already happens. This is called cold exergy. I'm going to give credit to my colleague Charles Gunderson, who we did the book with, one of the co-authors in the book. And most of his career looked at this in terms of exergy related systems in LNG. Okay, so he really, over his career, developed this theory very well. But I can also have a pressure sink, just like I have a heat sink. I can have a vacuum somewhere, like a low pressure reservoir, and I can allow air to come from the environment, go through a turbine, and enter my vacuum and produce work. None of these things are mystifying. These are all normal things. But I'll talk about later, but one of our main new contributions was really in this space. Okay, this is really what was unexplored well. So we take a look at heat exergy. You'll find a diagram that looks very similar like this if you just Google around. Basically, if I have temperature of heat in a generic abstract sense, this is my environmental temperature. You can compute the exergy as I get hotter, and then it approaches 1. And this is what's called exergy ratio. It's the exergy divided by the energy. Okay, so if I have, if I'm at 0.9 or 0.8, if I have 1,000 joules of heat, I have 900 joules of exergy of that heat. Okay, so that's what that means. The 0.9. Okay, it approaches 1, so infinitely hot temperature is pure exergy. If I go colder, you can see it increases extremely fast and goes above 1 and approaches infinity. And this is very inconvenient. People don't understand this. If you look, so many people just sort of conveniently stop the temperature there, so that way they don't have to think about it. All right, there's a lot of publications, they just kind of leave that part out. What it really means is the number you're dividing by is the wrong number. It's this number here, but the actual source of energy is not that, it's from the environment here. So if you divide it by that number, which is kind of invisible, it approaches 1, and 1 is the exergy ratio at absolute 0. So if you have a reservoir of infinitely cold stuff, every bit of energy you can produce is work. Okay, so you have real truth. These limits make thermodynamic sense. But this is a very simple thermodynamic result, and it gets a lot harder when you deal with real substances. But we can apply this, and we can see how this really does work in practice when it comes to real systems and real value. So these are utility costs in 2020 US dollars per gigajoule of service. So as a function of the temperature of that utility. All right, so if I have low pressure steam at like 120 roughly Celsius, it's roughly $4 per gigajoule of steam that I purchase. Okay, these numbers are out of Warren Cedars textbook. They're kind of like medians of his ranges, but these really come from sort of industrial survey and experiential data. And I'm just plotting his data basically. But you can kind of see that it kind of comes to a 0 at around, it turns out like 78 Celsius-ish. All right, this is, it's rough. But what that really means is that, the environment of your chemical plant, the surrounding temperature really isn't 25, it's really 78. Okay, it means that waste energy, you have enough waste heat floating around the sort of average chemical plant that it's not worth anything. You can't use it for anything valuable. It's kind of like a no-go zone. All right, and so that can become our reference condition for computing exergy of utilities, because that's kind of the true, from the sort of the measured data, like what we're seeing. All right, so all we have to do is you can compute the exergy of that utility, so it's the same ones as a function of temperature, and you can immediately see it follows that heat chart that I kind of showed before. Okay, it just follows it directly, and exergy gets very big as I go in the refrigeration space. And so I can just take that exergy of that utility. I'm going to plot it again against the cost on the previous slide. Okay, and I get this. All right, so here's my exergy of my utility, and then here's my cost. All right, and what we see is a dead linear correlation between the actual sort of survey cost of a utility on average and its thermodynamic exergy. All right, 0.998. It's basically $30 a gigajoule of exergy, like straight up for heat. Cooling is a different relationship, but if I use that plant ambient, I have this like direct, immediately correlated value that goes right down to zero, and it's absolutely remarkable, actually. It's a wonderful natural result that shows how exergy and value are so linked that money itself is related to exergy in this thermodynamic sense. That's a remarkable piece of information, and it's so useful. So we can use that in PSE for all sorts of stuff. All right, that's really cool. All right, in general, we know this anyways, chemical engineers. We know that things that have high exergy can do work. Okay, if I can use them to release energy and do work, and they result in low value streams. If I have a hot compressed gas, I can expand it, produce work, and then I have just a boring, weak atmospheric gas I can't do anything with. If I have something really hot, I can use a heat engine to make work. And then if I have an environmental stream, I can't do anything with environmental temperature. I can blend things to make interesting properties. I can release a chemical potential. I can burn stuff. And all of these I can do work. But to go backward, to go from low value to high exergy and high value, I need to consume a massive amount of work, right? To go away from ambient, I need to compress or pump. To temperature away from ambient, I need heating and utilities, either direction, up or down. Separations is a massively expensive thing, right? This a huge part of our industry is just how to do that. And creating chemicals with high energy is also very difficult, right? Really endothermic reactions and bonds requires a lot of work and a lot of energy to make that happen. But you can see it explicitly, and with chemical exergy, it's hard to appreciate just how high exergy certain chemicals are in fuels. So methane, natural gas, I can combust it and I can make heat and I can do all sorts of work with it. But then I get low value stuff. How do I get from low value stuff back into methane? Okay, like I could electrolyze water from the environment. I could use direct air capture of air to get CO2. I could electrolyze that. So I can get hydrogen, I get CO. I could do methane synthesis, right? Then I can separate out my chemicals and I could get methane. So this is a lot of work. It's something that people actually think about doing now in a hydrogen economy. But that's an incredible amount of work to go from the atmosphere to my substance, okay? But it goes both ways. Okay, so I'm going to talk just for a minute now about the classical thermomechanical exergy equation, because I think this is the most useful form that people can just use this equation quite directly in their own work. I think the hardest part is coming up with the values of H and S, but beyond that, the exergy of a substance, when you talk about just it's like temperature, pressure, phase, is very simple. I'm not going to go on the details, but you can make a simple thermodynamic model of like I have my substance, and if I'm going to have a magic box that produces work, and I'm going to sort of reject all of that to the environment. All right, and so you could do you could do mass and energy and quote unquote entropy balances on this, and solve for the case where you have complete reversibilities and you can compute the work. And I can do that for a different situation where I'm allowed, I have cold substance, so I can get heat from my environment. All right, and either way, you can do these balances, and this is a well-known thermodynamic exercise. We get this one nice equation. It's just the enthalpy of my thing subtracted from the enthalpy of that same thing at the environmental conditions, minus the entropy of that thing minus the same at the environmental conditions times my reference, my environmental temperature. Okay, it's a lot like a Gibbs free energy. It's not quite Gibbs free energy, but it's a very similar shape. Okay, so this is what we call the classical equation. I have my star here because this does break down. All right, and that's where I get into trouble a little bit. Okay, so that's the classical framework. And if I visualize this, all right, so here I have a pressure enthalpy diagram for a chemical. I picked butene because it was just a nice one, nice round numbers for me. And on here, you have your normal phase envelope. You've got vapor here, liquid here, and you have two-phase region inside. You have supercritical stuff up here. All right, these black lines are temperature, red lines are entropy. Those are all very normal, but now we have blue lines, and blue lines are exergy. Okay, using that equation, so thermomechanical exergy. So this dot here is my environment. So if I say 25 C1 atmosphere, I'm going to stick a dot there. That has 0 exergy. I can't do any useful work thermomechanically with that. Okay, so as I move away, if I go up in pressure, you can see the exergy goes up quite quickly. Okay, these are kilojoules per kilogram. If I go up in temperature, I need to go more in enthalpy per exergy, but that's okay. I can still go up in exergy if I go up in temperature. And if I go down in temperature, it goes up. All right, so if I'm moving away, then I should be gaining an exergy. And we have these kind of interesting shapes, like this kind of shape here. All right, this is really because exergy has to increase away from temperature. So here's from my atmospheric temperature. So here's my 25 C line. So I have to have this temperature increase away from the line here. Okay, so that's where that comes from. But that weird shape means I cannot use it in a thermodynamic tuple to define state. So if you don't know what that means, you're probably used to defining, you give someone temperature pressure or better temperature pressure phase, then I can plot the point, and then I know everything about that. Right? Or if I give you enthalpy pressure, I can plot the point, you know everything about it. If I give you density and entropy, you can plot the point, you know everything about it. But I can't do that with exergy. Okay, it's not monotonic and it's not unique for a given state variable, so I can't do that. But it's still an interesting point on that. I can read off the chart and I can get information and visualize it very, very well. But where you start to look now is you get a little suspicious here. Is if I go down in pressure, my exergy goes negative. Okay, and we'll talk about that in a bit. All right, but so here's a good example. All right, so let's say I have this butene at 2.1 bar 80 degrees C. I can plot it. All right, and then I can read off the exergy, and this is like this chart is right in exergy tables. Okay, it's going to be 40, and I can read it. Now I know my exergy, the thermomechanical exergy of that substance. All right, now this is calculated through the classical equation. But if I go way back to that optimization problem, I can show you a process that can give me 40 kilojoules per kilogram. Okay, this is one of them. I can expand isentropically a perfect gas turbine. And then I could use a perfect Carnot engine to produce additional work. And if you add the work produced there, which is just the enthalpy difference, and the work produced there, which is based on the Carnot efficiency, okay, I get 40. Okay, it's totally reproducible and well known, but it's not a unique path. Okay, so this path will solve the problem to provable optimality, but I could take this path too. I can just go down to 50 C at this pressure with a reversible heat engine, and then Carnot engine, and then I could do my expansion that way. And both of them give me exactly 40. All right, so it's not unique. I can go other ways. I can go all the way down to 25 and take an isothermal expansion that way. Okay, so all of them will give me the same number. So the answer is not unique to the optimization problem. All right, this is another way to look at it. We call this the Viking diagram because here in Norway. What we're looking at is the same information basically, but I have temperature and exergy on this axis, and then we have pressure as a parameter. So this black line here, this is just atmospheric pressure. Okay, so there's my reference condition. So that's my atmospheric temperature. So I'm at 0 exergy at that point. Then if I increase in temperature, I go this way. If I decrease, I'm going to go up in this direction. And then I start hitting phase changes. So I have a whole condensing phase here. All right, I cool down more, but then I'm melting now. And then once I get to the crystalline state, I'm cooling that until I level off and I hit a fixed boundary. It doesn't go to infinity. Okay, it actually goes to a fixed number. The reason for that is because of the third law of thermodynamics. And this is literally the only time in my life I've ever used the third law of thermodynamics. I don't even know if you know what it is, right? Yeah, John's laughing. I don't know. I don't want to ask him if he knows. But the third law of thermodynamics just says absolute entropy is 0 at absolute 0 Kelvin. The corollary is it means that I have to curve that way. That's what it means. My heat capacity approaches 0, and so I end up just not, going there. But the other, that's all it really means. But it's finite, and it stops. There's a limit. Okay, and these pressure lines collapse once I get into condensed phases. Okay, so all the contributions of pressure disappear once I get into condensed phases. And you're talking about now you have things like the very specific crystalline structure and variability of that matter. And in bulk, that doesn't matter. But now you can see like kind of the effect of the different variables in a plot more people like to see. Okay. So I'm going to give you some examples now of where we can actually use this. So if you get a good sense for Exergy, the book has a bunch of examples. I'm going to take you through a couple, just really short, just to give you a sense. But here's a real basic one. I have natural gas fired in a furnace. I'm going to use that to produce heat, to make steam. Okay, so I have air, gas, blow it up, flue gas comes out, I pump water, make steam. Super classic boiler. Okay, nothing special. All right, and all I did was I computed the exergy of these streams, which is really just lookup tables in the book. And I just sort of made the lines thick to kind of visualize it. All right, so real simple. This isn't hard to do, but you get a real good sense that the flow rates I had here, okay, this is my exergy of my fuel. All right, my electricity inputs are almost nothing. The exergy of the air is defined as 0. Water, there's really very, very little exergy here. All right, it's the fuel. The fuel is what matters, right? We know that implicitly, but it's confirmed here. All right, when I combust it, all right, I have my flue gas, which has, it's not 0, but there's a little bit of exergy in that. It's still hot. And then I have my heat, and then I'm use that to make steam. And so this heat gets transferred over here, and I can make 36 megajoules of exergy worth of steam for my 99 megajoules of exergy worth of my fuel. Okay, so you can trace the pathway, right, of your, and this is the pathway of value. All right, it's not joules of energy, it's really joules of value. That's the best way to think of it. All right, so there's a couple of things. If I look at the exergy efficiency of this, it's not that good. I take my product divided by my inputs. Okay, I'm just kind of roughing the numbers for you. But 99 plus I'm going to add all these numbers together, I get 35.5%. So I only capture 35.5%, 35.2% of the value of my fuel and all the other things I put into it in the form of steam. All right, and that's really, I mean, you could just see the value just diminishes and disappears, and you never get it again. That's called exergy destruction. Energy efficiency, it's a lot better. I don't know about you, but the furnace in my basement says, a sticker on it says 98. Okay, it's telling me it's 98% efficient. That's lower heating value. Higher heating value, it's 70%. Okay, so if I were to use the higher heating value of that fuel, okay, there, plus all the other junk, I'm going to get a value here that's the sort of like heat to vaporization kind of energy content. It's about 70%. Okay, so I'm getting 70% of the joules I put in. It's just I'm losing it in half of that in value, so much. All right, so you can see right away what's happening, but it brings up an existential crisis question. Like, should I be making steam with natural gas in the first place? So what this is really telling us is like, we could do so much better things with our natural gas. Can you please find a way to make steam out of something else? That would be better. All right, so burn trash or something, right? District heating. So this kind of tells you in terms of societal impacts now, we're starting to ask questions. We can just looking at the exergy, it's sort of like, really, should we do this? Okay, and if we do this, why is that a good idea? And you can trace this in a Sankey diagram. It's basically the same thing. So my energy flow, I'm getting basically 70 some odd % of my joules out from what I put in the fuel. I'm losing a bunch out the flue, of course. But in terms of exergy, I come in with 99. I'm only getting 30 out of steam at the end. All of this is absolutely lost. Okay, so never to be regained. This flue gas here, I could, for example, make a heat exchanger to capture the exergy off that flue gas, but it's only 8.8 megajoules a minute I could ever possibly get. No matter what I do, this part is completely lost. I can't even capture that. So this tells me, okay, if I were to make improvements, all right, I already know I'm losing energy out of the flue gas, but it's really low quality energy. So like, you know, maybe I don't need to build a heat exchanger. Maybe it's not worth it. Or if I do, this is a nice thermodynamic bound. Okay, so I don't know really. It's not an obvious solution. How I want to do that. In reality, I probably would. But we can see from the Exergy analysis that it's, it really puts things in perspective. All right, this loss Exergy is really telling us we're using high value stuff for low value product. Okay, you're just losing it. It's gone. Creating entropy you can't get back. All right, so in order to calculate these numbers in the book, we have tables of data for like the really big stuff and charts for everything else. So air and water, we have huge, think of like steam tables. Like steam tables are boring, they're super useful. So being able to just look up the Exergy of your most common things, super fast, super nice. But we also have chemical Exergies, which are really hard to compute because you have concentration impacts, you have chemical bond impacts, and it matters against reference conditions like how much bromine do you have in the ocean, and what, that kind of stuff is really tough for the normal person to deal with. So we do all that crap, and then you can just look up the Exergy number for chemical Exergy, and it's really fantastic. And we have it for thousands of chemicals. We have it for lots of common process streams that we get from industrial collaborations, concentrations, and things like that. So it's a really nice thing to take a look and just pull data so you can get right to the analysis. Another good example is direct air capture. Okay, so this is a hot topic in the environmental world. Should we spend very large amounts of, hopefully, CO2-free electricity to pull CO2 from the air and make it basically pure CO2 that we're going to sequester or do something with? Okay, so we can still use Exergy for very good thermodynamic bounds for this process. Okay, so we said Exergy is the maximum work you can get out of something, right? So thermodynamically speaking, that can only happen if it's a reversible process to get that work out. Flip that on its head, because it's reversible, Exergy is also the minimum amount of work it takes to get that thing from the environment. Okay, so if I have CO2 and I know it's Exergy, it's chemical Exergy. Okay, I can just look it up. There it is on my table. All right, it's about 20 kilojoules per mole. So their chemical Exergy, that's not chemical bond energy. That's really concentration differences with the environment. I should be able to exploit this, all right, somehow to produce work. But it's also the minimum, right? It's the minimum amount I have to spend to take CO2 from the environment and bring it up to pure CO2 at my environmental conditions, 25 C in 1 atmosphere. That doesn't include thermomechanical changes. That's just to deconcentrate it, to concentrate it, right? To undo the mixing of release. All right. It's a thermodynamic bound. Like you can't spend less than this to do the job. All right. Thermodynamically impossible. So what a fantastic bound for us to evaluate direct air capture, like just through the lookup table. All right, so if I go and I do this, and in the book we go over some existing examples of they're mostly all proposed design specs that we think we can get this. So they're very sort of generous. We're gonna use like air source heat pump for electricity, like all the things that would make it look good. We can get about 13% Exergy efficient to get CO2 out of the air and get it into uncompressed room temperature form at pure conditions. Okay, so there's a couple of things. 13% is a lot better than I personally thought it would be. I thought it would be like we'd be at 1%. 13% says, okay, we could be 6 times better in theory, but I mean, we'll never get there. But this tells you, okay, it's not the worst, and we can get better thermodynamically. We got a lot of room to grow. All right, but what a fantastic bound that we can use to evaluate the entire technology as a whole. Right? Super useful. And now I'm going to use another example. So let's say I have that CO2 and I want to compress it, put it in a pipeline to sequester. So that's something you could do. Okay, that's one of the reasons you pull it out of the air and stick it in the ground, for example. All right. So I'm going to start out with CO2 at 25 C in 1 atmosphere that I just got from my DSC, and there it is. Okay. It has 0 Exergy thermomechanically. Okay, it has chemical Exergy now, but now we're going to do thermomechanical changes. I want to get it up here. That's pipeline conditions there. 120 bar, just a little bit above atmospheric temperature. Okay, so that's about there. It's right on the 220 line. Kilojoules per kilogram. All right, that is the minimum work I have to do to get it there in a perfect lossless compression system. All right, so minimum 220, never can go lower. All right, what a fantastic bound for us. A real process looks like this. You have these multi-stage compressors with intermediate cooling, and you flash out water if you have any in there, depending on your, this is for a different example, but basically the same thing. And I want to get into sequestration ready conditions. All right. So in the book, we go through it. I need about 411 kilojoules per kilogram to run all these compressors. And these are real, sort of real compressors. These are not perfectly efficient compressors. They're sort of real systems. And that's not so terrible. It's about 53% Exergy efficient. Okay, so it means there's some room for improvement, but this is really expensive, and yeah, you can improve things here, but in reality, fighting against entropy like this at 50%, not so bad. Okay, so there's probably not a lot more we can do on this side. Last example, and this is exciting because it's not my work, it's Dr. Ebert's work. He's a professor in Bosnia, and he's came here to work with us on Exergy. What he does is heat integrated network synthesis problems. So like superstructure optimization, where you design the best water and energy network for heat exchange, mass exchange. And what he came to do, and one of the things he did here was, when working with us, is he started using Exergy as a proxy for cost. We already showed you how it could be utility differences, but what he managed to do is come up with a way to find an Exergy value that corresponds with the capital now. Okay, so in his innovation is really to use an Exergy loss due to friction, and he showed it correlates with network complexity in a general sense. So stream matches, sizes of exchangers, that kind of thing. It's a really good proxy for capital. And so he showed two things. One, the superstructure problem where you're minimizing Exergy loss is almost the same exact solution as minimizing cost. Okay, annualized cost with capital and operating together. The difference is the Exergy part relaxed the problem from an MINLP to an NLP. If you know what that means, it means it's way the heck easier to solve, and know the answer is right there. So this is fantastic. So this is in press now, but this is a wonderful application that he did. So we're really excited about what he's been able to do, and he keeps working in this space. So this is where I think the future is going. I'm looking at the time, John. I need about 4 or 5 minutes. I'll let you decide. Otherwise, I'm going to end it here. But I have a couple more things I would like to share, but I'll let you call it.
Well, let's do this. I think this is fantastic. I think we got a little bit of time. Why don't we go four more minutes, and then we'll.
I think that's about what I need. So, okay, so I'm going to break down a year's worth of research that I'm putting my career at risk and providing to you. So in 4 minutes, so hopefully I do justice, okay? So the main thing is really examining, as I mentioned before, that thermomechanical Exergy below atmospheric pressure, okay? So I tried to show you that it was negative, okay? If you do the calculation, it's absolutely negative. Like you type in that in the equation, absolutely. Like that part's not in question. If I just blindly type in my enthalpies and entropies, okay? So basically, this is what we had to challenge, is the status quo on that equation. And the truth is that so few people have looked at this problem that it's easy to understand why it kind of made it through. All right. So I'm going to go right back to my definition. It's the maximum theoretical work you can do. Okay. And I have my optimization problem. Again, I just want to bring that right back up, and I'm going to find the process that gives me the maximum work. I'm just going to put that back in your head. Okay. I'm going to also repeat the slide of this model. Okay, but and this is the equation I have again. And one more time to visualize everything. Okay, you have this negative Exergy. Okay, I'm just showing you the same slides I already showed you. So I have 0 here, and I have negative here. Okay, now that doesn't make any sense to me, because if I have something that's 0 Exergy, it means I can do no work with it. But it also means it costs me no work to make it perfectly thermodynamically. So in theory, I should be able to move from my lukewarm state, 25C1 bar, anywhere along this line for free. Right? That doesn't make any sense. So this is what caused me significant pause. But this has been discussed. I'm not the first person to bring this up, that's for sure. So my argument is negative Exergy cannot be the solution to the optimization problem. Okay, you can't have negative. And it's easy because I can provide a lower bound through a counterexample, right? And if you're an optimization PSC person, this makes total sense to you. Okay, I can always find a process that equilibrates my system at zero work. Okay, so if I have my vacuum, all right, my thing's sitting in a glass jar, my process is I'm going to punch a hole in it and just let it sit there. Given infinite time, that thing's going to fill with the environment air, right? It equilibrates and it does no work. So zero is at least one solution to that problem. But it's definitely not the max, but it's definitely not the min. It's more than negative, okay? So this is from the optimization perspective, I just don't see how that could ever be the case from the definition. So there's one book, CODAS, and there's a whole community of people that have this position, okay? And this is gonna be a little interesting. All right, so this comes out of his book, and all right, they have this kind of TP diagram, and you see I had the Viking plot, it's the same thing. So T exergy, okay, atmospheric above it. I don't disagree with any of this, but here, below pressure, the plot goes negative, it comes back up. Forget about the phase issues, forget about the third law of dynamics. I'm only gonna care about the negative part right now. Okay, well, that's that problem with that figure. Okay, and so CODAS goes to explain this, to prove it. Why is it negative? And he said, okay, I'm going to postulate this process. It's completely reversible. I'm going to use the fact that it's, some temperature difference in the environment to drive a heat engine. All right, it's going to make work for me. Okay, I agree there. It's off temperature. And then I'm going to use that work to drive a compressor, which is going to generate that vacuum for me upstream. Okay, so that's how you would generate a vacuum. And if you do the math, you get a negative number because you have more work in the compressor than in your generation here. And so the conclusion he makes is therefore it produces because it produces negative work, therefore exergy is negative. But I say no, it just means that your process is not the solution to the optimization problem. Like, yes, you postulated a P, but it's not the exergy. Okay, so what happened, because it gives you exactly the classical equation, actually. All right. So what happened? Basically, if you go back to this original model that everybody uses, it's the start of every single Exergy textbook. There's something really important missing, is that there's no ability in this generic form for mass to leave the environment and join with the substance to go into my magic box. And because of that, we have arbitrarily constrained our optimization problem. Okay. In an optimization context, it makes total sense. We have constrained away the solutions that would solve it in a normal situation. Okay, so if we eliminate that constraint, then we should be able to find the new solution. Okay, this is what I mean, is this is not general enough below atmospheric pressure. So we re-derived everything, and we found it easier to flip the problem. Okay, to explain it is that the exergy is the minimum work it takes to go from my reference state to the environment. Right, it's a thermodynamically equivalent problem. Okay, if I go back to this example, okay, yeah, I break it up into a state star. I know the work it takes to go from here to here, which is a compressor or expander, reversible, and I know this is a reversible heat pump. All right, and so I can also go backward. It doesn't matter, it's the same. I can do either one, and they all arrive at the same equation. So the optimization route, if I postulate these P's, they actually verify the classical result. Okay, so if provably, the classical result is the optimal solution with pressures at and above reference temperature. Okay, even though it's non-unique, but I can also pose the Q that goes the reverse direction, and I get the same things. But if I go down, all right, what I need is basically a heat pump, and then I need to do isentropic expansion, doing work to kind of create this vacuum, right, against boundary conditions. And that's also just the entropy difference, enthalpy difference here. So if I just take these two steps, and any process will do, as we know there's non-unique solutions, I just have my first step, which is just the classical equation, which everyone agrees with, plus this enthalpy difference, which is also just very classic thermodynamics, just reversible change in pressure isentropically, and we add them together and we get our new equation. And it looks weird because it's absolute value, but that's just to reflect the fact that I need different technologies to go in both directions. This reduces everything above atmospheric, this reduces to the classical, and below it, it's a little different. If I replot it now, all right, now I have something that makes total sense. I have my dot, my zero, and everything gets bigger away from it in this fashion. Okay, and it's not smooth here with reference to sensitivities, but that's because I'm switching machines itself. All right, so it makes total sense. We saw that same non-smoothness in the heat curve, right? We saw it go down and then sharply go up in a totally different direction. So that's already built into the system. We already have a system switch. Okay, so that's the fundamental challenge, is that we need to use a different equation below this. Everybody's fine. Whatever you've been doing above it, you're fine. Okay, but if you're exploring this new space, we need something different. Okay, so that's basically it. So I want to thank you very much. Buy the book. I'm happy to answer any questions as well.
Okay, fantastic. Well, thank you, Tom. Let's give him a round of applause. Thank you. Okay. I have a question here from Jonathan. He says, I found the second example you presented on direct air capture especially intriguing. It highlighted a crucial area of focus within the realm of carbon capture technologies. I'm keen to explore further. Specifically, I'm interested in understanding the intricacies of Exergy losses throughout the DAC process. Could you shed light on the main sources of these Exergy losses and discuss potential strategies for minimizing them? Additionally, I'm curious about the significance of Exergy analysis within the life cycle assessment of this. How would it contribute to evaluating environmental and operational efficiency of these systems?
All right, that sounds like a PhD thesis question. That's amazing.
Right.
Okay, so real short, in calculating the number, the book goes over the details a little bit, but you basically need heat and you need electricity to run it. I mean, that's at the end of the day. So, you know, in my calculation, I'm being as generous as I can with things like heat pumps, which are the best way to use electricity to generate heat at certain degrees, because you get to extract heat from the environment as well, stuff like that. But in terms of the finite details, I don't know enough about the minutia of how the CO2 might be adsorbed to an adsorbent, adsorb, desorb, right? The fundamental problem is you're going against concentration differences, pressure differences, and temperature differences. You know, you're talking about 400, 450 parts per million CO2 you want to bring to pure, right? That's a huge change. So it's just naturally a very difficult process. Your bigger picture question about life cycle, I mean, obviously it has to be no CO2 emissions associated with the life cycle. Otherwise you completely kill everything. And it also answers big picture questions about where we should spend our money. Okay, so a big part of my research program is on eco-techno-economic analysis. That's what John was trying to say in the beginning of the talk. And, it basically means, how do you compare, you know, the money with the environment? And one of the biggest things that we want to calculate is something something's called the cost of CO2 avoided. And you kind of flip it on its head. You know, what we try to do is we try to answer, what's the best way to spend $1 trillion on climate change technology? Okay, avoidance, right? Do you want to spend $1 trillion on direct air capture? Or do you want to spend $1 trillion on maybe CO2 capture from power plant and some biofuels? All right, that is going to tell you, and the Exergy differential is going to help you decide, okay, if I'm going to only spend $1 trillion and I want to avoid the most CO2, you pluck the lowest hanging fruit. All right, as much as we hate it, the cheapest way to use our money, the best way to use our money to get the most CO2 out now, is either power capture from a power plant or bulldoze every coal plant and replace it with a natural gas plant. You can spend $1 trillion doing that, and your CO2 reduction will be far better than if you built $1 trillion in DAC. Okay, and you can look at the Exergy to help you decide that. All right, so you're asking like a super big question that's literally like the whole focus of my research program. So I think I just have to stop there to avoid getting out of control.
Fantastic. Well, let's time for maybe one more question. And just while they're thinking of that, Tom, Exergy tables like steam tables and others, you know, they're fantastic. You go to a reference book, you look them up. Sometimes having them digitally is really nice as well. Just so you know you're working on things as part of a program that you're writing. Any plans to make these digitally available as well?
Yeah, I mean, they're digital and access engineering in the sense that they're, you know, HTML in the sense that you can extract from that. But we're working on the sort of the Python libraries to do that. But there's certain rights behind how you, like the thermodynamics. So the calculations of the Exergy is not super hard when you've done all the work for reference states, when you've kind of programmed everything, and you have access to good thermodynamic models. That's the really hard part.
Mhm.
Okay, so that's where you're really limited because you have to basically build a thermodynamic package that encompasses every unique chemical specialty. So it's a big task, which is why we have tables
Yeah, that makes sense.
at the moment. Yeah,
Okay.
so
Well,
it's in
fantastic.
progress. Yeah.
Okay. Well, great. Any last burning questions? Okay. Well, thanks again, Tom. We will post these, this recording later today, and I really appreciate your presentation today.
All right. Thanks, John. Thanks, everybody.